So let's look at this in terms of equations. Estimating a parameter using confidence intervals. Suppose we want to estimate the mean mu of a normal population using the sample average x bar as the estimator. Using the observed value of x bar, we create an interval such that the mean is greater than or equal to x bar minus a constant and less than or equal to x bar plus a constant equal to 1 minus alpha, the confidence coefficient. And this should be, as we were saying before, a big number, like 95%, 99%. This interval, x bar plus or minus k, a constant, is called a 1 minus alpha percent confidence interval for the mean. 1 minus alpha we call the confidence coefficient, and of course k, this is what we're interested in. K is determining the size of the interval. This is determined from the distribution of the estimator x bar, which we know. So just one more time though, the interpretation of the confidence interval is that if a large number of each of such intervals are constructed, each resulting from a random variable, then 1 minus alpha percent of these intervals will contain the true population value for the mean, or for the parameter that you're looking for. So let's, in this section, we're only going to look at the confidence interval for the mean of a normal population when sigma is known. So if we have a population which is normally distributed with a mean mu and a variance sigma squared, then the sample average x bar, which is also a random variable, is distributed with the same mean mu, but with a variance of sigma squared divided by n. And we learned that in the earlier sections when we talked about the central limit theorem. And don't forget here, of course, n is the sample size. Now, we learned also that we can transform our random variable into a z variable, that should be a comma, by subtracting its mean and dividing by its standard deviation, which we have here. And this transformed variable will be centered about 0, mean of 0, and a standard deviation of 1. So using this result, the 1 minus alpha 100% confidence interval for mu is obtained according to the following formula. Our random variable x bar plus or minus alpha z alpha over 2 times the standard deviation sigma over the square root of n, where sigma is the known standard deviation and z alpha over 2 is such that the probability that the random variable z is greater than the z alpha over 2 value is equal to alpha over 2. And I show this on the next page. So again, we are looking for the confidence interval for the mean of a normal population with known sigma using the sample average as an estimator. First, we take a sample and we calculate, so we have a sample n, we calculate an x bar value, and we know that this is normally distributed mean sigma over the square root of n, where sigma is the population standard deviation. We transform this variable by subtracting the mean and dividing by the standard deviation, and we can look at how this standard normal distribution looks up. We can look this up on our table. So it has a mean of 0, a standard deviation of 1. Now, we have chosen a confidence interval of 1 minus alpha. Let's say we've chosen a big high number like 95%. And what we need to do now, using our standard normal tables, is to identify the z values, the z alpha over 2 values, so that 95%, there's a 95% probability that the random variable z will lie between these two z alpha over 2 values. And a very small percentage, only alpha over 2, the probability that our z values will lie beyond our 2v values will be a very small percentage, which is alpha over 2. And we then calculate, according to our formula there, the confidence interval. We know the x bar. We know the z alpha over 2 because we just looked that up. And of course, we know n, and we know the standard deviation of our population. So let's do an example, then it will be very clear. So we have a random sample of 4 bottles of fabric softener taken from a day's production. And the amount of turbidity in them was measured in parts per million. And turbidity is the cloudiness or haziness of a fluid caused by particles. And it's a very important quality measurement, quality test for water quality. So we have 4 different values, n equals 4, of turbidity in parts per million measured on a certain day. Now, we need to find the 99% confidence interval that the mean turbidity of the population of bottles filled on this line of that day based on our sample. Now, and we also know we're given that the turbidity measurements are normally distributed and have a standard deviation of sigma equals 0.3. So we had the confidence interval given as x bar plus or minus z alpha over 2 times sigma over the square root of n. Now, we can calculate this, we're given this, and we know this. Let's look a little more closely at how we come up with z alpha over 2. And in this case, we have 1 minus alpha equals 99%, or alpha equals 1%. So here we have our, do you remember these tables? Remember how to read these? This is the cumulative probability, the probability that random variable z is less than or equal to a certain fixed value, where the z values you read first down this way and then this way. So we need a 99% confidence interval for the mean turbidity in all the bottles of fabric softener filled in a line. So 1 minus alpha equals 0.99. This means alpha equals 1%, or alpha over 2 equals 0.5% or 0.005. If you remember from our picture that we had earlier, these will be the 2 little tails of the distribution. So if I can draw that up here, if we have our standard normal table, 0 and 1, we are looking for the z values, z alpha over 2 minus z alpha over 2, where these small little tails, the probability that our random variable z will be either greater or less than those z values will be just alpha over 2. So alpha over 2 is here 0.005. But from this table, this is the probability that the random variable is less than or equal to z. So in this case, this table will give us this entire probability here. And so what we're looking for then, the probability that random variable z is less than or equal to z is going to be equal to 0.995. So we look for 0.995, and what I can see here is that it's lying right midway between 0.9949 and 0.9951. So I read my z value, I get z equals 2.5, 2.57, 2.58, so 2.575, right in the middle. And what this means that at 2.575, I will only have 0.005% probability that the random variable will be larger than 2.575. Maybe you can look at that again yourselves. Just remind yourselves how to use that table. But the goal here was to find these two z alpha over 2 values. So going back to our example. So we need a 99% confidence interval for the mean turbidity of all the bottles of fabric softener filled in the line. Sigma is known to be 0.3. We had a sample of 4 bottles, and we've already calculated then that for 1 minus alpha equals 0.99, z alpha over 2 is going to be 2.575. Now, our x bar, if you add those numbers up and divide by 4, you will get 13, and we have a standard deviation of 0.3 that was given. So now we have all the elements we need for our confidence interval. We get alpha, we have x bar, we have z, we have sigma, and we have the square root of n. So 13 minus 2.575 times 0.3 over the square root of 4, and 13 plus 2.575 times 0.3 over the square root of 4. And if we look at that, we end up getting a confidence interval of 12.61 and 13.39 parts per million from this sample. So let's look again. What is the interpretation of this confidence interval? So we have measured on one day different values of turbidity, and we have come up with an x bar value of 13. We are looking for the mean turbidity for all the bottles produced that day. We know it's not 13 because we just took a sample of 4, but we can construct a confidence interval around that 13 so that we are here with this confidence interval, 12.61 to 13.39, we are 99% confidence that our true mean lies within that interval. And another way of looking at it, if we measured every day for 100 days the mean turbidity, we would have 100 different samples. With a 99% confidence interval, on 99 out of those 100 days, each different confidence interval that we calculate will contain the true population mean. But on one day, it will not. So I hope that's clear. Let's just look at one last thing. What are the factors to reduce the margin of error or tighten the confidence interval? So I draw this picture again. Here we have some alphas, our confidence interval, x bar minus an x bar plus constant k. We know how to calculate that. Here's a picture. The z alpha over 2 values are defined, of course, by the 1 minus alpha probability within those 2 values. What do we have to work with? What would you do if you wanted to make this k value smaller? So I can see 3 parameters. The first one might be the most obvious. If you increase the sample size, n is in the denominator, this means that our k value will get smaller. And so when we take a sample with our big sample size, with a certain level of confidence, we will have a smaller confidence interval, and we can be more certain about the distribution of our population. But what's the problem with that? What's the problem with increasing the sample size? I think probably you're thinking about cost, or in Germany, we've got euros. Thinking of the cost for the time to take the samples. If it's a sampling that's destructive, you end up losing product. So the cost goes up. So what else could we do? Well, we've got the sample standard deviation here. We could reduce that, and that would be great. What does reducing standard deviation mean? If we reduce the standard deviation of our population, we're improving the process. We're reducing the variability. This is great. This would improve everything, our yield, everything. But what's the problem for this? I mean, first of all, yes, it costs money. So you can also say it costs money. But at some point, you cannot get rid of all the variability in your production. There's too many inputs. There's too many things that go into making the product. So it's not possible maybe to reduce this value to get the confidence interval range that you like. So then we have one more. Can anyone think what else we could do? I mean, you should all be eyeing our z values here. Now you think, great. If I reduce my z values, I can reduce my confidence interval. How do you do that? You need to decrease the 1 minus alpha. You need to make this probability smaller. But what does that do? The problem there, of course, is that then you only have an 80% confidence that your confidence interval based on your sample contains the true population mean. And so if you can live with it, that's fine. But otherwise, it means that from your all the measurements that you're taking, all the turbidity measurements on 100 days, only 80 of those days will contain a true mean and 20 of those days will not. So that might end up leading to problems with your conclusions based on your sample. Okay, just one more point. We did this first example, the confidence interval for the mean of a normal population when sigma is known. But of course, in many cases, sigma is not known. It must be estimated using the sample. So in this case, I'd ask you to refer to our textbook. It's the same procedure, and you can see there how confidence intervals are calculated for this case. We are also interested in other parameters, for example, the variance of a population. We can construct confidence intervals also using other techniques there, and these two are both in our book. And you can construct confidence intervals for the number of defects in a population, for example, or for the process capability of a population, and so forth. But the important point of this lecture is to understand why confidence intervals are useful and how we can use our statistics knowledge to construct meaningful confidence intervals from our sample measurements.